Yes.
Take it away.
Ooh. All right. Everybody have a beer? Yep. That's good for me. All right. I have to stand here. I thought I would escape. All right. Can you hear me okay? This is really awkward to stand here, but I'll do my best. Okay. So my name is Alneng, and I represent a company called Ekkono Solutions, and we do machine learning for IoT, very specifically for edge computing. I'll get back to that. But to challenge myself a little bit, and since it's not a sales pitch, I'm going to talk about sustainable machine learning. Does that sound interesting to you guys? Okay, I'll try to make it as interesting as possible for you. So, since I go first, I get to choose what's the definition of machine learning. So I found this on Wikipedia. Computational learning using algorithms to learn from and make predictions on data. So data is sort of the king here, and that's what we're trying to do. There's a joke on the side, but we won't have time to look at that right now. Machine learning is something that's been going on for a long time. It's nothing new, I think, already from the 60s or something. But then there were some breakthroughs or funky stuff that was going on. First one that everybody sort of saw was this one up here. Does anybody know what that is? Deep Blue. Yeah, so Deep Blue, Garry Kasparov at that time. Now it's, I think, a Norwegian guy, but it used to be Garry Kasparov being the best chess player in the world. And in 1996, he got to play against Deep Blue, and he won. So there was some hope for humanity still, right? Then a year later, 97, that was in Philadelphia, and then a year later in New York, he played Deep Blue again and lost. So there goes that. And you know that what happens is that when a machine beats you, you will never win against it again. So and now there's no hope for humanity on that one. A little bit later in 2016, Google came up with this DeepMind, or I think DeepMind existed when they bought it, but they were playing a much more complex game called Go. And if you haven't seen it, I really recommend that I put the, I know you can't see it, but the link down there. But on YouTube, there is a documentary about how they sort of cracked the code and played against this guy over here, DC Gold. And everybody thought he would win 5-0. He thought so. I mean, his whole aim was not to lose one single game. That was his first. Then it started and he lost 3 in a row. So he was super depressed. And whole Korea, I think, almost went down with it. And then he managed to win one, so there was some hope for humanity again, and then he lost so it was 4-1. But as you can see, it was easy goal, 1 human brain and maybe a cup of coffee against 100 and something data scientists coming together and a lot of processing power in play so that they could actually beat it, but they did. And as I said, the documentary is really worthwhile looking at. So, what this boils down to is that we have a lot of technology, we can do a lot of really, really funny stuff with it, but we have to be sort of careful because it actually needs a lot of energy to work. So here you have a trip from New York to San Francisco, about 200 pounds of CO2, and that's the CO2 emission from that flight. Then average human life, 11,000 pounds. Then American life seems to be much more fun because they have 36,000 pounds of CO2 on 1 year. And an average car in the US, in its lifetime, so this is not even a year, it's a lifetime, does away with 126,000 tons of CO2. And then we have the example here with Transformer, which is a neural architecture for speech recognition, I think. And you can see that is almost five times or 4.5 times as much as you would have from using the car for a whole lifetime. So, as I said, we have to sort of be a little bit aware of using this technology in the right way. And then we at Ekkono start to look at this. We actually have, from last week, a PhD in energy effective algorithms, Eva. And we're looking, this is a data set that's a standard data set that everybody can find and try out. We tried this with deep learning and then with some other technologies, more energy efficient. And as you can see, we have up here the accuracy, and we have here obviously the energy that it uses. And it's even more clear over here that we can actually use technologies that are not as energy hungry, but still get almost the same or better accuracy than. So we have to sort of always choose what's best when it comes to using this. And for us, that's particularly important because we're residing at the edge, and there are very few resources, and there might even be a battery on the other side. So we won't drain that battery through using the wrong type of machine learning. Important stuff. Right, so when we talk about edge, and some of you might have seen this before, but it's sort of important to remember that edge is not better than cloud, and cloud is not better than edge. They're good at different things. But there are a few things that are important when we talk about edge machine learning. The shareable data volume, there's no way you can send all that data up to the cloud. So what you do is that you send average data. Average daily data, hourly data, but it's not all the data. It's never all the data. So if you send average data from here to here and create an average model over here and then send back that average model, the whole loop is sort of average, which is not the best thing. Then you have a latency problem if you want to take real-time actions. You have connectivity problem. We have a lot of customers doing marine environments where connectivity is not a given. And data integrity here in Sweden, we don't even have to talk about, right? So what I want to concentrate on is energy efficiency and this thing over here, which is individualization, because I think those goes really well together. So when we talk about individualization, and it actually says incremental learning over here that I'm covering that. So what is incremental learning? Well, you've known from the first slide there that machine learning is learning from data sets and then predicting the future, right? Everybody still with me there? Good. What you can do here in a very constrained environment is that you can keep on learning. So it's not like you make a model and then you put it on the edge and then it lives there and then you send it to a cloud, you make it better and send it back. Here, it's constantly learning. It's taking streaming data and it creates a pipeline and it learns from that. So it becomes tailor-made for this specific car in this specific environment. And for this specific car, let's say that it's the same apart from the color. It learns its environment. So it becomes absolutely tailor-made to that one. It's not average in any respect, right? So, what is the sustainability gain of using machine learning at the edge with incremental learning? Are you thinking about that? If you didn't, then I'm sort of stuck here. No? So, I'll continue. I'll give you 3 examples of how I think that this could play really, really well together, and then we will judge if I'm right or wrong. First example there is around predictive maintenance on heat exchangers. Second one is the performance optimization on gas turbines. And the last one is battery management on electric vehicles or buses. Okay? So let's look at the first one. This is a heat exchanger. Industrial heat exchangers, they are very much used all over the world, very effective. What we wanted to do here was that these ones, they have liquid coming in, liquid coming out, and then there's a place where they actually meet each other and exchange the temperature. And all these plates, they get dirty or fouled over a certain amount of time. So one example where it's dairy products where it takes 1 day and then it's all fouled, and you have to rinse it and use it again. But you have other cases where it takes 5 years, maybe it's water, and it takes 5 years for this whole process to go through. When are you supposed to clean it? Well, if you use machine learning on the device, incrementally understanding the health of the system, then we can build sort of a virtual sensor that tells you the efficiency, something you couldn't measure. You can measure here the temperature, on 2 sides, you can measure the pressure, and through that you can correlate and see what is exactly the efficiency of the heat exchanger at any given moment, which gives you the possibility of actually acting when it's time to act, not before and that's certainly not after the fact that it's become foul. But it's still sitting on the device, understanding the device, incrementally learn about the device, and then act upon what is out there. Okay? And it has a tremendous effect if it comes to sustainable. So there's actually a study made that if you would use this on all heat exchangers in the whole world, which are quite a few, you actually could influence the CO2 emissions by about 2.5%. So all of a sudden you have a real sustainability gain from doing this. Not only that the operator can do this at the right time, you can also save sort of the environment through doing this in the right way. Second example, this is a gas turbine. It looks small here, but it's gigantic in real life. And here it's more about optimizing, understanding the environment. Again, incrementally learn about this. I think there's 30 or 40 parameters that you have to look and get exactly right. And when you get it right, then all of a sudden you bring down the NOx emission by the equivalent of thousands of cars. So it's a real gain on sustainability. It's a real gain of sitting in the right place and incrementally learn about this value here. And the last one is about buses. Does anybody here, I know this is, but does anybody here have an electric car or something like that? Yeah. You drive differently when you drive your electric car than you did before?
Somebody does, definitely.
Yeah, because my understanding is that when you get all this knowledge, it's not driving as fast as possible, it's sort of driving as efficient as possible. Yes. So getting information about health and range all of a sudden makes your driving different. You adapt to that. This is sort of the gain that you get from this, apart from understanding the whole life cycle of the battery and trying to maximize the output of the battery. And that was it.
Great. So making sure it's clear to keep the pace and everything, did you stand there while Johan, our next speaker, is ready? And we take some questions for you.
Yeah.
Are you ready for that? Any questions for Anders? Yes. You always present yourself.
Is it about your husband?
No, it's not. It's about the life science sector. So I'm Lucy J. Risch, my consultancy. I come from a genome world of big data.
Yeah.
Do you feel that the machine learning and the future of the healthcare is going as quickly as it should do, or do you feel that we're still quite behind with machine learning?
That's a good question. It's not a bit really broad question, but I actually have a good friend who works in emergency. And when you get into emergency, you have this thing that you look up to, and there's like 7 critical measurements, right? I don't know what it is. What's the name of that type of machine?
Blood pressure analysis.
Right, yeah. And then there are some alarms when they reach over the threshold and the doctor comes out. Combined with these, I understand that that's not very in terms at all, but it goes on quite a lot. If you can actually learn the doctor's behavior and understand when there is something critical going on or not, then you can actually do something really, really interesting. So I think it should be used more. Then obviously, I know that from the public sector in Sweden, these things move slow.
Yeah, because I like your theory about obviously learning more as you go by.
Yes.
I think that's a great analogy, actually.
Yeah, it is. We have a customer called Husqvarna. They have this automower, lawnmower, and that was sort of an idea of spot there. That my colleague has one, and it's been running around for 7,000 pound hours, but it hasn't learned anything about the garden. So having it learn, reinforcement learning about where it gets stuck over vacations or when to spot a toddler on the lawn, that could be really interesting. So building that kind of intelligence is really interesting.
And is that actually happening? Are we?
Oh, exactly. Yeah, it's happening in a lot of places.
But not necessarily in the healthcare business.
I don't think it is.
I can add in there. Yeah, I'm just another speaker for later, but since I actually I'm on the board of a healthcare company, a predictive healthcare company, I can say that for Sweden, it's tremendously bad. We throw away huge amounts of data, or in other cases, we take in data. And we actually, the CEO of that company, he said it's like putting information into a shredder. The Ekkono system, whatever that is called. But it's really, really bad in Sweden for a lot of situations. So we were super behind, and now they're in the south at least implementing a new Ekkono system, and that's going to take 2 years before they can do anything in certain areas. And So we're really behind on that. Let's see. The US is actually better there, for instance.
Well, we have to stop you there.
All right.
It's a very good topic.
Yeah,
Thank you so much.
maybe we can have a future.
Yeah, we have more. We have a lot of meetings on. So our next speaker is Johan from Imagimob.
I'm supposed to stand here all the time for a movie.
We can move 3 centimeters to the left.
Okay. Perfect. Yeah, so my name is Johan Malm. I work as a machine learning engineer and developer at Imagimob here in Stockholm. And the title of this talk is From Data Collection to Embedded AI Application. So I'm going to use a project that we did last fall with a company called Ekkono from Lund. And I will show you how we did this project from the very start to the final application. As you all know, you are interested in machine learning and you're data scientists. How many in here are data scientists? Yeah? Okay, I won't go to. No, but as you all know, we live in a world of data. There is a lot of value in this data, but we need a tool to be able to leverage on this because raw data in massive amounts, it's impossible for a human to understand it and interpret it. So machine learning has as previous speaker said, it started a long time ago, but it's the last couple of years that we're really seeing that the big value increase here. So this value is also now starting to move. It's not only up in the connected businesses. It starts to move to the physical world, and I really like that because I think that that's where we are going to make a better world and make a big difference. Netflix recommendations, it's not like the thing I think will solve all the problems. But the real world is complex in the way that it's not digitalized yet. So we don't have access to all this data. And to have that, we need to connect to the sensors. So we need to start the data collection ourselves usually. And once we have data, we need to build the application. We need to port it to such a little device, and that's complex work. So usually, some estimates say that embedded software development takes on the order of 10 to 20 times more time than usual desktop software development. So it's a complex and time-consuming work. So the project that we did together with Ekkono was this. So we used their radar system, which is the world's smallest radar. It's a really impressive sensor. And we used that signal to interpret gestures. And the target for this was to come up with 4 robust gestures that we and the target platform was a small MCU of type ARM Cortex M4, and the deadline was the CES demo in Las Vegas. So that was the format of the project. And then maybe you may ask yourself, why do we need these gestures? Well, there are a couple of interesting use cases, not only entertainment and consumer electronics, but also hygiene and like clean industry. Very hot now in these days. The safety, to be able to monitor what you do in cars, for instance, without letting your hands off the steering wheel. So there are a number of use cases, but this is more like speculation still because it's a new thing. So if we take a step back, we got some introduction here. What is machine learning? And basically, this is what it is. So it's given some input x, we want to learn a function that takes this input x to some output. So it's very simple. And in the past, we did this by a lot of mathematical modeling, solving PDEs and so on. I spent 5 years here at KTH solving PDEs. That's great, but limited. So what you can do now, if you have these x and y pairs, you can learn the function f. And the x and y means you need to collect this data. So once you have that, you can learn this function x, f. And number 3 is not everybody has to go all that way, but deploy to this little MCU is actually a lot of work if you don't do it efficiently. Okay, so the first step, which may seem trivial, is actually just get the data out of the sensor. So what you typically do is you buy the sensor with some development board that you can plug into your PC, for instance, with a USB cable. And this is the test rig that we built. So we just put the radar on top of these earphones, and then we have the data on the PC. The next thing you need to do is to label the data. So you need to say, okay, this gesture, this piece of data means this, and this piece of data means this, and so on. And that also may seem trivial, but if you imagine you have a lot of data and you want to minimize the manual work here, you have to do this very efficiently. Otherwise, you spend like 90% of your work in this area. And with sensor data, it looks like this. This is from an accelerometer. So you cannot just look at it and say, okay, that was jumping. This was walking. You have to attach something to it. And what we do is we have a tool called Imagimob Capture, which is a Android app. So you use the camera on the phone to take a movie of in this case gesture, but it could be whatever you want to capture. And when you do that, the sensor is streaming data to the phone. So you save the data plus the video times it. So in that way you can easily see what you are actually recording, and you can label that. So we have buttons here that you can push and put the label directly. And then you can connect your data stream like this. So the data goes from the sensor to your PC. And from the PC, we have like the server sending the data to the phone. And from the phone, we store it in a cloud storage. And then when we want to build the model, we just download the data. It's organized, it's labeled. And in this particular case, here I'm sitting, collecting data. So I put the phone like this, and I have it in selfie mode. And I do the gesture. The data goes here to the cable, to the PC, and then from the PC to the phone. Okay, so when quite often you need to fine-tune your labels because maybe it was a little bit too late, or I mean the timing was not perfect. So what you don't want to do in this case is to go manually into text files and edit lines because that will consume a lot of time. So what you would like to have is some kind of graphical tool. So what you see here is the gesture. So in the video data, here you see the signal, and here is the label. And you can take your mouse and tune this label. And when it's done, you just press Ctrl S, and then you're done. Okay, so the next step, now you have all the data in place. You have fixed with the label, so everything looks perfect. The next thing is that you want to train some model. And you can do it you can use many different types. What we focus on is neural networks. So some kind of deep learning. It depends how many layers we usually use, but with this tool you can select how many type of structure you want to search through, and then how many types of hyperparameters to search through, and then you start training on cluster, and the job goes off to a GPU cluster and searches all these models, and then you get the result with each model and the accuracy for each model, so you can pick the best one. So maybe you're done there. You can plot everything in a nice confusion matrix. But what you would like to do if you build some kind of real-time application is to somehow get to know the timing of your application. So what we can do is we read the model back into the studio, and then we compare the manual set label with the label that the model thinks it is. So we can compare these two lines here. And what can happen is that you have some mix-up. So here we did one gesture, but the model thought it was something else. So we sorted those gestures out of the way. And then we came down to four different gestures that we tested in a demo. And this is also quite important, I think, to quickly build a live demo, so you can really test and see the real-time feel of it. And what you notice here is okay, it works kind of well, but sometimes it doesn't work. So this was not good enough for the final demo, and then what you maybe you've seen can come to this situation. The accuracy seems kind of stuck on a certain level. You have tried all different models, but you don't know what to do. So in this case, you need to rethink the whole problem. So in our case, one of the problems was that the gestures were, we defined the gestures, right? So, but like after the first iteration, we realized, okay, that they are too big. So if the model fails, you need to go down and start over. So it may seem easy, but we realized that, okay, let's do shorter gestures. So if you fail or the model fails and have a low probability output, we just ignore that, and then we take the next one, and the user just continues until the application responds. So that was one positive thing. The other benefit was that having a small gesture means that you can use little input data, which makes the model smaller, and also you get the response from the model much quicker. So you get the faster feedback. All right, so we came up with a bunch of short gestures, and here is you see some of the data. This data is quite complex, as I said, for a human to understand. But again, we define gestures. We define which gestures to use. So we could actually take the ones that were furthest apart. So in this reduced dimensional plot, we could select 4 that we used in the final version. So here we built again a PC demo, and now we started to get to something that works really well. So this is still PC, but it works very well. The next step after this is to then translate to an MCU, and so to go from Python to C is usually a pain, actually. You get all strange bugs, memory bugs and stuff like that. And I did some of that painful work, but now the tools are more mature, and what we can do is we take an H5 model that is saved from TensorFlow, and this on this edge tab here, we can just generate C code automatically with very easily. So in this project, we then got a static C library that we could integrate into this processor, and this is the final demo. Look how glad you are when you have done this work. These are the 4 gestures. Supposed to be sound here. Now they look quite big, of course, but this was just a demo, and in the real product, you can imagine that this radar it can sit behind plastic, so you can integrate it into a small in-ear thing because the radar is tiny. But yeah, I see here. Okay.
So let's leave the desk for you, Martin, and have you any questions, Johan, or was that completely clear? Any specific steps there where you missed? Or? Yes. And who are you? Sorry.
I'm sorry. You gave the deadline, but you didn't give the start of the project.
The start of the project was around the summer. That was when we teamed up with Ekkono, and they presented the data. We looked at the data, and we started the first iteration.
Radio? You ready?
Not really. It's all black. But
Now we're ready. Okay.
Okay, there is one more.
One more question.
Yes, my name is Kenny. I'm nobody but what made you narrow down on those 4 gestures? Was it purely the shortness of it, or did you have some success rate identifying?
No, the final demo had four gestures.
Yeah. What made you narrow down on those 4 gestures?
Huh?
What made you select those 4?
Because they were far apart in this 2D plot that you saw, so they were very different in some respects. So that made it, of course, easier. But we also wanted to have something that potentially could steer music, previous song and next song, and so connected to some logic inside the data.
Great. Thank you so much. And our next speaker, asking from Sentian. Take it away, Martin.
Hi guys, nice to be here. Right, so I'm from Sentian.AI, I'm the CEO and founder, and I'm going to talk about transformation through AI. And I want to start with an interesting case. So this is Ant Financial Services Group. It's a part of the Alibaba Group. It's their PayPal, if you put it that way. They're currently valued at $150 billion, which is not bad for a 5-year-old startup. One might even call them a scale-up by now. So that I think is a fairly impressive trajectory as a company. So what's interesting about AI and financial services? Well, the thing is that what they've done is they've incorporated AI all over the whole business. So the whole company is effectively run by an AI. They take data from their data streams or payment stream and all of the apps that they and services that they've created, and use that data in order to create new services on top of the other services, and etc. And this goes on and on. And what they've done is that they've been able to take away people from the daily operations of running these services. So all of their stuff is really about creating new apps and new services that can reuse that data and putting models around it and creating an AI that, yes, continuously evolves. So that's what they do. And one could say that they are the roadmap for the future when it comes to financial services. So that's why I think they're very interesting, because I believe that there is a roadmap effectively everywhere for all industries and all aspects. And what I've put together here for the more heavy industry and put together some thoughts of what kind of roadmaps we're looking at when it comes to different opportunities. And I'm focusing very much on classic industry, the industry, because we work a lot with the industry. So if we take an area like manufacturing, there's a great opportunity to improve quality control. You can shorten these design cycles using AI. You can remove the supply chain bottlenecks. You can reduce the materials and the energy waste when you're building things. You can optimize the maintenance. You can detect production anomalies and system anomalies and problems that way. You can go to cobots. You can have reduced variation. I'll talk a little bit more about that in a while. And create intelligent control system around this. So effectively adding AI to the automation systems and so on. And that's just one area. Let's pick maintenance areas. So you see, there's a huge amount of things. And for each area of the industry, you can do the same. And if you would replace these by the other services like e-commerce, or if you put healthcare, as we had before, there are roadmaps for all of these areas. And the sum, if you put it that way, from all of these is huge benefits to these companies in terms of reducing cost, improving efficiency, and creating new services. So revenue boosting also. So you can do a lot with this. And companies need to start working on this. And so I'll just take another perspective of things, because I meet a lot of companies when I'm out talking to them. And my experience, and I've actually seen some reports that have the same conclusion, that when we look at European companies, or to be more precise, Swedish and German companies, there's around 70% of these industrial companies, they're just thinking about what they should be doing with AI. They're not actually doing it. They may be collecting a bit of data, but they're really stuck in this. What should we do? How should we do this? Should we buy or build, or should we what kind of governance should we have around? What is the business case for this? So they're very much stuck there. Another 25% is really in the POC phase. So having lots of POCs, or at least one POC, trying to learn about what they can do with AI. And then finally, there's about 5% that has actually implemented things. I'm slightly worried about that because AI is very, very driven from experience today. You have to get your hands dirty. You have to start doing things. When you started doing things, you can learn about the next step and find opportunities that you can do after that. And there's also obviously the data thing. The more data you have, the better service you can run, the better service you have, the better models you can build. Better models will give you more data and more customers, and it's a virtuous cycle going up. So that accounts both for the data side of it, but also the experience side of things. Just to put another perspective of things, where we with patents when it comes to AI. So most of them are done in China. And that's something that we in the Nordics may need to be a bit concerned about. This is for patent filings from the academic side, but there's out of our perspectives. And it's not good, to put it that way. What we're doing in Europe is we're protecting ourselves. We're challenging these AI patents instead of actually trying to do them ourselves. Another perspective, which I think is rather interesting, because we're looking at accelerating returns when it comes to AI, is that if we compress, or if we look at the evolution of the 1900 to 2000, so 100 years of development, and take that as a baseline and see how fast are we developing now. So we had 100 years to do that, and if we look at the first 14 years after 2000, we managed to squeeze in another 100 years of development. And we're right now on track to squeeze in another 100 years of development with that baseline until 2021. So things are going a lot quicker. And if you're not getting into what we're going to do with AI, I mean, start implementing and doing things with it, you're going to get behind on this. And there are certain countries that are not getting behind on this. Another perspective that I thought could be interesting to just reflect a little bit of. When you have a new technology that's coming out, the first thing that happens is that the consulting world starts to pick up on it. Because you don't know really what to do, you have to try out things. So they're very successful right now. For good reasons, they need to do things, and companies need to learn and get moving. After a little while, you start to find these areas where you can build products. And eventually you start to get open source. So where do we stand right now? Well, there are some products out there. There's products in the area of predictive maintenance. There are products in the area of anomaly detection and quality control using image recognition. I'm talking about the industrial applications now. There are other ones for e-commerce and so on. And they're starting to get new ones like control system optimization and robotics and other niche products. Open source, that's mainly in the area of having tools today, but eventually we'll get there. And there's going to be more products coming up after a while to populate as soon as we've learned more about this. And there will be diminishing returns on the consultancy side over time. Right, so one can think about this. Is AI a project or is it strategic? And I think all companies need to ponder on what they are doing, because it's clearly strategic, but at the same time you've got to get moving on doing things, so it's also a project. Right, so I'm now getting into a case talking about a German company that we have, and want to talk about something that is, I was just stratospheric recently, or in my talk a few minutes ago. I'm not going to get down to the low level of very operational systems. So we're talking about variation reduction or adding intelligence to automation systems. And in this case, it's for improved quality. So what's variation to start off with? Because obviously the difference within a range of measurements and results. And when you have a process, a manufacturing process or another process, it's very, very important to take away as much variation so you can get as close as the ideal state as possible. And if you don't, you can have more or less important problems. And the Problems are in quality, in customer satisfaction, in scrap, and so on. So it's an important thing. In this particular customer, they're making high-tech sensors, and it's a precision product in a complicated process. And they wanted to improve the accuracy of that process in order to improve their quality. The problem they had was they had lack of data. The variation differed over time, and it's drifted, if you put it that way. And the sources of variation were complex. It wasn't clear exactly where it comes from. It came from different things at different points of time. And there was a lag time in the process from measurements. So this is actually the process. There was lots of steps in it, and we got in on that step. And what we did was that we used a solution where we could try to find and create a solution that would adapt to these process variations that occur naturally in the process, so that we could correct for those changes and keep the process at its peak. And the way they had done it previous to us was that they had a PhD guy make some calculations on it, and they had a bunch of guys from the operations that helped out and tried to find that model that would work for them. And we replaced it with this system. And it uses a lot of different models to come up with the right predictions and implications and other things that you need in this process. And eventually we could create this recommendation for how the settings would be. We're currently at recommendations, so they change it manually, but we're probably going to go to automation at a later stage. One other thing that might be interesting to note here, we use automatic ML. So if you don't know what automatic ML is, it's basically having an AI that teaches the models in the AI how to do it. So that reduces the time for us to develop the service, and it also helps out with adding new angles to the problem and how you solve it. So in total, system was deployed last year, so it's live and it's being used. So it's one of those 5%, if you put it that way. It has had a huge impact on very, very small change in their process. They've managed to squeeze out 20% more of A-quality products for them, which is huge for them. And we've made a system that handles these updates that are necessary as the system learns more and get more data points. And we're applying it to other sensors now. So you can look at these. These are some other examples. If you take that perspective of a roadmap, talking, for instance, about power industry, where you can you burn something, you boil water, and you distribute that water into a city as heat, and you can do things with them in all steps. So you can do an improved or optimized process of how you burn the fuel. You can improve the forecasting for how much energy that should be distributed into the city. And you can do predictive maintenance on the whole area. And for each of these areas, if you run a big power plant, there are huge savings to be made or increases in revenues. Let's have some examples. Just rounding off with a few words about who we are. So from a company called Sentian, we do industrial solutions, some of our customers, and yeah, we have products in the area of predictive maintenance and anomaly detection, control systems, and all of these examples that I've been mentioning so far. So that's us. Yeah.
Erik is preparing himself. We have some questions for you, I'm sure. Yes. How are you? We know you from here.
So, did we usually run your greatness in the cloud or on a PC next to the?
We run mainly on the cloud. Yeah.
More questions? Yes.
How is artificial intelligence going to help smarter homes?
smarter homes?
Yeah.
Well, there's a lot of things you can do with that. Let's start with heating. So in the Nordics, we build very robust houses. So they maintain a very constant temperature. But taking the example of heat distribution for a power plant, what they can do is they connect themselves to the house. It's a multi-tenant house with a little valve in the cellar. They can direct the heat from the radiators to the water, and save massive amounts of energy that they otherwise need to get out of a peak load. Because between 7 and 9 o'clock in the morning, you have a peak load because people are taking showers, effectively. And if there's a lot of inertia in the building, so they keep hot. So you don't, if you turn off the radiator for 2 hours, you won't notice that in Sweden. And that's the Nordic case. If you go to the US, you don't want to have your AC running when it's hot, daytime, but you still want it to be cold when you get home in the evening, rather than having an hour of having that blast in cold coming out. And if you can get your AC to start working just half an hour or 45 minutes before you get home, you can get that out of the way, and people will not run it the whole day. And things like that. That's just a few examples. That was just the heat example of one place.
I will continue the whole evening to talk about that, because now Erik is ready. So, and there's actually a dynamic duo here. Johan is also good. So, take it away, guys. Stream analyze.
Thank you.
Thank you.
Right. Do we fit in the picture?
That's the most important thing.
Just getting closer. Okay. Hello, everyone. Thanks for the introduction. I'm Erik, Zeitler. I'm co-founder of Stream.AI. I got my colleague, Johan Risch, with me.
Hi, I'm Johan Risch. I'm a developer of Stream.AI, and I do a lot of the customer projects as well.
Yeah, great. So we heard before that we had a problem of squeezing 100 years of development into 7 years. We might have one or two things to say about that. Just bear with us. So why is this important? Yeah, you heard all the pep talk already. This will be significant. How to do it then? We put ML in the funnel and you will be AI compliant, right? So to further articulate this a bit, there is a lot of thought work into best practices and so on. This is stolen with pride from Microsoft Azure. You see on the left-hand side you have the raw data coming in, and then you do these magical tricks, and eventually you come up with a rather good model. So we have been interested in how to come up with that model, and we might have a few words to say on tools and processes. So this double loop essentially captures the conventional development process with data collection. You set up a lab, you collect some data, you store it on a Kafka or on a USB stick, you take that USB stick, do some analysis offline, perhaps upload it into the cloud, you evaluate, refine, and then you do a data collection all over again. What we do instead is that we install Stream.AI software on the edge devices, and you can start querying those devices directly instead. So you can start interacting with your fleet. And that's the lower loop of it. So you go basically from days or weeks to minutes in the development process. And we believe this is going to be important if you want to squeeze 700 years into 7 years. Right. Essentially our software enables agile analytics and machine learning on edge devices, if you like. And you can also look at the machine learning and edge analytics process refinement of that as a few stages. So at the first stage, you want to know how the product is being used, and then basically you should queries at the edge devices. The second stage is, okay, how does this and this usage lead to wear and tear? And then you start understanding what's going on, given the measurements, what is the outcome. And once you start having an understanding, you can also build these models. And when you see that the models do work, you can start considering automation. Yeah, in order to get on top of things, let's see if we can get our hands dirty with a use case. So Johan, can you tell us what's going on here?
Yeah, so we ran a project. We were running on a chainsaw, and the hardware was running in this project was a D32, which is a small MCU with about 4 MB of memory. And we ran that with FreeRTO was in the bottom and then SE engine on top of that, connected via Wi-Fi via mobile phones, so we could actually connect to the cloud and interact in development with this. The system had 3 sensors which were made beforehand, so we had an engineer in our customer's place where they had actually worked with this kind of setup for about 8 years and had gotten nowhere essentially. They hadn't really gotten to any stage where more or less have a theory of the data but not really using data or actually analyzing it for real. And the 3 sensors was a RPM sensor, revolutions per minute. There was a acoustic emission sensor, a E sensor, which essentially measured peaks in friction sound to detect like high frequency sounds above 250 kilohertz, and also a temperature sensor to measure the temperature of the blade.
Right. So the first thing we started doing when we got started on this project was to have a look at the I'm going back here for a while. Have a look at this hardware and trying to figure out, okay, can our data stream management system actually run on this? Yes, it could. So as soon as we say, yes, it can run here, then also we had the full query language and the full analysis system available to us on that hardware platform. So there is basically no need of recompiling any machine learning or any queries. It just works. So the first thing we want to do then is start using the chainsaw or the fleet of chainsaws, if you like, and start extracting data. So again, this is not about collecting data and saving it for later. This is about extracting data and looking at what's happening right now. And yeah, just to remind you, we had, so what kind of use cases were we extracting data for? In this case, we had the nose clear bucking, we had the bore cut, and we had no load full throttle. Can you tell us about these exciting chainsaw usages?
Yeah, sure. So we had, as I said, we started each test set with a few seconds of full throttle no load, so just pushing the button, just letting the chainsaw run. Then we did 3 of these bore cut, this nose clear buckets, which essentially you're cutting through the log essentially. And then in the final set we did nose clear buckets, which essentially sticking in the chainsaw into the log. And we did the same kind of sequence every time to be able to look at data and understand it and see kind of variations in it depending on settings, lubrications, if you compare them with each other.
That sounds great. And you soon came up with some measurements, I understand.
Right. Yeah, sure. Sorry. So this is like a typical slide you saw here. So you can see we start here in the left part with a full throttle no load. Then we've got a few nose clear buckings, a few bore cuts, and then a final full throttle no load there. And the blue graph is the acoustic emission pulses, and the orange graph is the temperature, which is two of the sensors we're using. We're going to get more details, but we only have 2 here in a few minutes.
Right, so you guys were sitting in the same lab and were extracting these signals, or tell me about the development process here.
Well, yeah, so he was in the lumber yard at their company, and I was sitting in Uppsala, and I was actually collecting data from my site while he was doing this. He's in full gear, doing cutting and everything in the live stream. So this data was essentially sent to me before I heard the actual chainsaw running on the device. So I was recording data as we're actually working with it.
So you mean the speed of the network was higher than the speed of the sound?
Yes.
Yeah. That's good. So once you start to get a grip on the data and start to understand what's going on in each of these usage patterns, then you can start trying to understand. Okay, do we have any correlations between the measurements? Can we see what outcome it leads to? Can we see anything about the wear and tear, for instance? Do we know when it's time to lubricate the chain? Because that's one of the things you need to do from time to time when using a chainsaw. Again, I want to remind you about this these cycles, that we want to stay in this more tight loop where you focus on modeling, deploying, evaluating, and refine your model, rather than focusing on the infrastructure and making things work, because with Stream Analyze the infrastructure is already there. So what we saw also was that there was a fair amount of queries and correlations on these variables, and there was a fair amount of testing. In fact, I heard that the amount of testing was so vast in comparison to what he did during the previous 7 years. So they ran into sensor quality issues actually that they didn't see before. Can you tell us a bit more about that?
Yeah, so the first issue we encountered was that, okay, so we had used a kind of optoelectrical unit to measure the RPM on like a reflection plate on the engine. And this was the first time we ran on an electric chainsaw. An electric chainsaw does not vibrate as much as a petrol chainsaw. So what we actually had to realize was that the RPM sensor did not work on an electric chainsaw because there become a lot of sawdust inside the engine there, so the sensor would stop working.
Sågspån in Swedish.
Yeah. So we actually had to skip the RPM sensor. And our biggest hope here from our engineer was to actually find the correlation between the RPM and the actual friction sound. That was like the main thesis he had for a lot of years there. So we had to rethink this, and we said, okay, let's try just looking at the peaks. You have kind of nice patterns on the acoustic emissions. We might be able to use temperature as well just to get some kind of conclusion for this project. Because we only had 6 weeks in total for this whole project from connecting the sensors to actually develop the model and showing it in the live demo. So we started looking at the acoustic emissions, and you can see the blue line here over a test over 1 day. We ran so much testing here that we realized that the sensor for acoustic emissions degraded with temperature change. So it actually started to give us less and less data until we had no data left actually from the acoustic emissions. So we were left with temperature. And, you know, when you working with temperature over slow sensor here, you're going to use a very simple model, which essentially end up being a simple differentiation over time. But let's just talk a bit about what I'm all listening in there for you first.
Right, thanks. Okay, so once you have found these correlations with one or more sensors, you will want to have this model deployed and maintained somehow. And you will want to use the model to monitor the equipment, and you will also want to monitor the execution of the model. And again, using stream analyze software on the edge devices, you'll stay in this tight loop where the infrastructure is already taken care of. So you can focus on the model. And yeah, did I mention the query language? Yes, I think I did. So here's an example of the query language, which actually is the meaty parts of the model, as far as I understood, on this chainsaw use case. Perhaps you can shed some more light on this.
Yeah, we're not going to go through a lot of details of the language here, but it's essentially the full model was about 50 lines of code, including documentation of the code of what it does as well. So, and all in all, you see it's a query language like SQL, but it's combined with MATLAB, and SQL has been proven to be very good for transforming and filtering data. That is why it's in the most serious databases in the world. But you do not want to do Fourier analysis or deep learning inside SQL because it's a bunch of limitations you don't want to use it for. But we have an extendable query language working on objects where you can create your own data type, and we also have all of the most common data types in the system from the get-go. So you work in a query language where you're filtering and doing transformations and calculations over vectors, matrices, tensors, char strings, JSON objects, CSV rows, whatever you want there. And you can, if you have your favorite data type, you can always plug it in afterwards using your extended system here. And what you get in the end is, with the query language in this high-level mode, is that you're not working with how to do the model. You're saying you have essentially the equation system. You're giving the system, our system, the constraints for how to do the queries on the data stream, and in turn you get out a model which can tell you how the chainsaw is working. And the only difference between the deep learning model in our system and this model would be that you would, instead of doing divided intensity time, they would have one would be essentially classify the input vector and get a given output vector as a classification. So there's a different, essentially a different function call in that part.
I know that here we do actually compute the derivative of the temperature with reflection time, right? Detempi time, and detempi time is the function over there. Okay, moving on. And this AE, you actually use the acceleration sensor to some extent, right?
Yeah, we used to just create a binary sensor. We could actually see that we got some pulses. We knew that the chainsaw was actually running. So we just used it as a binary sensor telling us if it was running or not.
So the acceleration was almost there, but still a little light. So you could use it.
Yeah.
Fair enough. That's fine. Yeah, and eventually, once you've seen, okay, yeah, I want to go back here and ask you, did the model work?
Yes, it did actually quite well.
So this model could tell you that, okay, it's time for lubrication of the chain, right?
Yeah. And that was mainly due to the engineer we used at the company was very, very good with the friction and the temperature, how it performed the chains. So he could very easily set the correct threshold for when the derivative of the temperature was too high, too steep, and the temperature was too high. He knew they would have to do something with the lubrication there. So that's something you really need to make experts' knowledge to do. I could never have done it myself. I would have needed a lot of labor training there to do it.
I think it's pretty good when you can actually understand your model.
So do I.
That's just an opinion. That's yeah, I happen to have an opinion. Okay, so once you have this model, the model seems to work. Then you can also start discussing. Okay, do I want to do predictive maintenance or do I want to do automatic maintenance? And for us, the only difference between that is actually add an actuator step one way or another. In this case, it would be an automatic lubrication of the chain. With that, I think we're pretty much done.
First of all, it was a nice approach with two speakers, and among them, one of the most fast-speaking persons I know. It's just amazing how you can move your lips so fast. Any questions for you guys? Yes.
I think one from the side. I wonder if you could compare how well would it perform just taking a temperature model against creating your own model without really knowing.
That's a good question, and that's something we actually had in the proposed next steps in that project, and we're still working on the next steps because we'll be allocated to another division there. But essentially, that was actually when we tried to compare, because we never had time to compare with it with the next steps of temperature there. So I can say this, I don't know. But that's really the next part to compare.
No, there was a question here for behind you.
Nicholas Ferman, podcast and public speaker. Who would you say is taking on the lead when it comes to this kind of refining process in products today?
So like what role in the company?
No, which kind of products or companies are taking the lead when it comes to this kind of refining process when it comes to ML?
You, I think.
Good question.
Except for your chainsaw. So.
Yeah, good question. I think this is a challenge for everyone, and it's also a challenge for any business and enterprise to spend some good time thinking of what kind of not only tools but also teams and processes do I want to employ. The graph we showed early on from Microsoft Azure actually, sadly enough, indicated that the machine learning process is some kind of thing you can divide into steps. And that will imply for most business and enterprise consultants that we form a team around this, another team around this, and another team around this. And I think we claim that, sorry for poking my hand in your face, I'm making these gestures, you know. I think we claim that if you look at this process as a unified approach rather, that's the way you more easily can cram those 100 years into 7 years. I don't know if that was an answer to your question.
Good enough.
Yeah, good enough.
Now we have to move forward. Thank you so much.
Thank you.
To our last but not least speaker, our favorite here in the building actually, Greenlytics. Mihai, take it away.
Thank you very much for the introduction and the opportunity. My name is Mihai, and I'm a co-founder and CTO at Greenlytics. And at Greenlytics, we do weather analytics for the power industry. We like to think about our company as sitting at the intersection between meteorology, the energy system, and data science. And this is because in our team we are passionate about data science, and we also have very good backgrounds on the energy system. And if you look at the value chain that we work with every day, we start from raw data, which we collect from the different utility companies, transform it, extract information out of the raw data, because raw data as itself is not really useful. Extract information that is becoming descriptive, and then out of the information we want to gain insights that is reasonable about the models within data, and then it becomes predictive. Then we can make the forecast and predictions about actually the value, the true value comes when we actually can take decisions from those predictive models. So that's when we transform, data becomes prescriptive. At Greenlytics, we focus more on the right side of the value chain, trying to transform, trying to derive data from descriptive, predictive, and to prescriptive. So basically to build decision support tools for the energy industry. And we started out with a power forecast for the renewable energy sources. We developed initially wind mine and solar mine, which are basically forecasting tools for the renewable energy generation. I'm going to take wind power forecasting as a use case here, and because I think it's quite relevant to the meeting, to the event today. And if you think about how can we answer to this question, how much wind power will be produced in Sweden tomorrow, hour by hour? So now we have a use case, but let me tell you why this is important. Well, in the electricity grid, in order to function properly, it needs to be in a constant balance between production and consumption. On the production side, you typically had regular CHP, combined heat and power plants, nuclear power plants, gas turbines, and so on, which you could easily tweak how much they would produce. They were very predictable. But once we replace this energy source, these energy plants with renewable based energy plants, they will depend more and more on weather. And that, as we all know, the weather is not unpredictable, but uncertain, will cause uncertainty in the power production. So keeping the grid in balance is going to become a much harder task in the future once we have more and more renewable energy. You would say maybe that's a bad thing. Maybe we shouldn't have enough. We shouldn't have renewable energy as much because we're hurting the grid. Well, actually, we could. It's fine to increase a lot the penetration of renewable energy as long as we can develop the proper tools to keep the balance. And this is how we use machine learning within our company to try to achieve. Renewable energy, as I said, forecasting really depends on the weather, and actually on the weather forecasts. And the weather forecasts that we need to take into our system, it's actually quite big data. We have different numerical weather models that do the forecasts every day, or actually multiple times per day. Every model has many different variables like temperature, pressure, and so on. And of course, we have the entire grid imagine the entire grid of the world, where maybe you have a model that has a resolution of like 6 kilometers or 10 kilometers. Imagine the number of points that you need to have for the entire globe. So that can easily become in the order of trillion of data points per day. And this is just about the weather. Now the challenge is actually to use this weather forecast for our use case to try to predict how much wind power will Sweden generate tomorrow. And this information will help a lot the TSO, the transmission system operator. This is quite a challenging task, because imagine that Sweden is it's a decently big country, and you have a lot of wind power, which is spread across the country. And typically what we think is that, okay, we need to know the locations of all the wind parks in Sweden, and the capacity, and the terrain, all that information, right? So it becomes a really big challenge just to build up your data set, to build up all this information. What we actually want in the end is the aggregated forecast. This is what the transmission system operator needs, is the aggregated power of this of all these wind farms. And then we said, why don't we turn to machine learning and try to feed it with the weather maps, with the weather data, and let it learn where the wind parks are located, how big they are, what is the terrain, what are the specifications of that. Just by having the raw or meteorological forecast and a map, and the actual total aggregated power to train on as the target. And we did that. We did not build any manual features from the weather variables. We simply built a neural network architecture that can extract automatically features from the weather forecasts and map it out to our aggregated power signal that we need to forecast. And I'm actually going to skip this, and I'm going to show you the demo. We actually have a page where we describe this. This is the power data. This is how like the power signal, the produced power for one of the pricing regions here in Sweden looks like. This is in megawatts, and this is just an example of our yearly production of wind power for pricing region AC1. And then what we did is that we start from the raw meteorological forecast data as a map, as a grid, see the entire Sweden and actually the entire Nordic part. And the target is actually to the forecast of this wind power production. And that is this forecast for the next 2 days. And as you can see here, whenever we have like weather front coming in like this, you'll have increased production in energy. But then we said, okay, this is fine, but neural networks they have this. They're well known that they're black boxes. So we just say, but is it really working? I mean, sure, we get the kind of this we can forecast, but what does it actually do? And then we said, okay, let's try to open the box and look inside. And it was very good to find out that when we did that, we actually discovered that since let me show you how the pricing regions in Sweden. Sweden is divided here. It's divided in 4 different pricing regions. AC1 here in the north, AC2 in the middle, 3 in the Stockholm region or south region, and AC4 is the southernmost pricing region. And what we have found out was that without specifying the model where these pricing regions are, it actually learned that Sweden, the region 1 is up here in the north, the region 2 is here in the middle, region 3, and region 4. So this actually shows that the model did learn the correlations. And if we look at these heat maps, you actually see that they are sometimes different here. This is like low resolution, but they do actually correlate with locations of the high capacity wind parks that are situated here in the south or in the AC3 or AC2. So this actually gave us confidence that the model did discover the main producers, the main wind farms, and it actually does work as we wanted. And we can see that while the weather fronts develop, these heat maps, they're actually not very stable because they can follow the different small regions of high or low production, but they always keep within the correct pricing region or electricity region that we forecast for. And as I said before, this is really quite a big data challenge problem, and we can't be really done without massive distributed computing. And for that we use auto-scaling clusters and a lot of compute infrastructure from Amazon Web Services. This is our team. We have Henrik and Vincent here as well, and Sebastian unfortunately cannot attend this event today. Yeah. No,
What will the weather be tomorrow?
Historical data.
Yes.
How much historical data do you use? And then, what was it the data just around the part?
it was this entire map here. Yes.
On what?
Resolution 2.5 kilometers.
Okay.
So it's quite a big grid, and it's 2.5 kilometers in terms of weather forecast, like American weather forecast, is quite high resolution. Yeah, let's say.
Okay, so historical data.
Exactly, like 1 year or 1 year and a half.
Okay, and then when did you like say, okay, now we know the weather for the next day? Was it like the day before or 3 days before?
We usually forecast like 3 days ahead.
Okay.
Questions? Of course.
Thank you.
Who are you?
Lucy, Robert Shaw. If I have solar panels on my roof, how do I know how much sun there will be tomorrow, so that I know how much is actually coming down into my solar panels?
Well, I mean, have different.
Have you?
Yes, we do solar power forecast as well.
Okay. Do you do that to the individual person, or is it a corporate business you sell that to?
No, we do that. Not to individual person, but we have like smaller customers, let's say like this. Typically, you either have a physical forecast where you look at your panel specifications and take the solar radiation and compute the estimated power. But if you have historical data, then we do machine learning, and we don't need the specifications. We just learn how much it will produce based on the historical production and the weather forecasts.
And if you go back 5 years, how is there more? Are we producing more solar power than we were?
I mean, yes, all renewable energy sources are increasing a lot. So yeah, compared to what they were producing 5 years ago, it's definitely much more.
One more question. Yes.
My name is Erik. I work as a consultant with Zeitler. I have a question. You mentioned about how black you work with stars. I just wanted to do some model validation to
Any what? Model?
Validation of the model. So how do you do it?
Yes, of course. I mean, this is the validation mode. This is a part of the model development process. You always split your data set into train, validation, and test, and you compute all your metrics on your test. It's actually what we see here, for example. These are the forecasts on the test set. So it was not really where we have trained it for. This is data that the model wasn't trained for, and we saw that it performs well.
Great. So the little I know, I have a question for you. The little I know of this. When will we know what weather will be tomorrow? Will it then? Your model will work better, I guess.
Tomorrow you'll know how the weather will be.
Well, raining in Cope. Right.
Just assume what the weather will be tomorrow.
Thank you, Johan. So, thank you. Not only are the speakers spectacular in what they know and what they've told us today, they also kept on time very, very well. You have to appreciate that. Secondly, I always say this, I really, really admire people who know a lot and share that to others, where you supposed to, and I think they're working very good for that. Now it's time to grab another beer, and the different people will be around the tables and go and taste them. We are here normally until 9.
Stop the recording.